Hello, my dear students. Welcome again in this class of statistical mechanics. So, as you all know that in our previous lecture we have discussed about the density matrix and density operator, and then we have derived the expression for this time dependence of this density matrix using the Schrodinger wave equation and proved the Lively's theorem for this quantum statistical treatment. So in this today's lecture, we will derive the expression of a density matrix for this microcanonical, canonical, and grand canonical ensemble. So starting with this microcanonical ensemble. So let me select pen. So in the microcanonical ensemble, as you all know that the construction of microcanonical ensemble, it is based on the promise that the system constituting the ensemble which are characterized by a fixed number of particle, so that is n having fixed volume, and the energy which lying between the interval, so which varies from E minus delta by 2 to E plus delta by 2. So where this slight change in energy, that is delta, it is very less as compared to the total energy of this system. So the total number of distinct microstates which are accessible to this system for this microcanonical ensemble, so they are related with this n, v, e, and delta, and their microstates that is generally represented with this sigma. So the assumption which enters in this microcanonical ensemble theory, it is generally referred to as the postulate of equal a prior probability for various accessible states. So for this microcanonical ensemble, there are two postulates which have been derived. The second postulate is a postulate of random a prior phase. So equal a prior probability and equal a prior phase. So these are the two postulates which we generally consider for this microcanonical ensemble. And so in this ensemble, which consists of the various systems in this state, and we generally represent this system as a wave function alpha psi. So where alpha which varies from 1, 2, 3 up to n number of systems which are present in this microcanonical ensemble. Now, if the system is closed and isolated, then this wave function psi, it can be taken to these energy eigen functions. So we can write this relation. So if we apply this operator h to this wave function, and we can write this equation, that is E alpha into psi alpha, where E alpha, these are the eigenvalues of these energy, and psi alpha, that is generally known as the eigen function. So let us say this is our equation number 1. So from this we can write down the time dependence of this density matrix, so which we have derived in our previous lecture, that is I h bar curly rho over curly t, so that is equal to minus rho h commutator. Now if the system they are independent of this time, then the value of this curly rho over curly t, if we consider it to be the time independent function, then the value of this curly rho over curly t, it comes out to be 0. So in this case, so we can write the relation of this density with respect to this energy function, that is equal to 0. So what does it mean? So let us say this is our equation number second. Now from this equation number 3, so it means that the rho and h they commute. So therefore in this case the density matrix rho, it is associated with some constant of motion of the system. So the possibility is that this density is some function of h. So from this equation, so driving the expression with respect to this equation of motion, so this density, it is some sort of function of this h. So we can write the value of this rho as a rho of h, where this rho of h, when we expand this in terms of a power series, then we can write this rho of h is a naught plus a1 h plus a2 h square, where a, they are generally known as the wave amplitude, and so and so. So the density matrix, when we choose these energy eigenfunction as basic vector, so we can write the value of this density matrix for two systems n and m. So something like rho of n star into density of h psi of m into d tau, where d tau is the characterized volume. So using this equation, so let us say this is our equation number 4. So using this equation 1, so we can write down this equation 4 as rho of h into psi n, that is equal to rho of en, that is this density. It is a function of energy into psi n. So let us say this is our equation number 5. So putting the value of this density as a function of energy, so our density operator Nm, so this becomes the density of En into integration of n star into psi n into d tau. So this we can write down as a density of En into this is n and this is m. So this is a canonical delta function nm. Now this canonical delta function, so it has a two value. So when delta of nm, it is equal to 1, when m is equal to n, and it is equal to 0 for m which is not equal to n. Hence in this energy, so this delta h, it is a diagonal matrix. So here this rho of En, it is the probability of observing these eigenvalues En if a measurement of energy is made on a particular system which we choose at random, and we can write the value of this rho En, so that is equal to this probability density function omega of n. So let us say this is equation number 6. So from this equation it follows that in the case of these degenerate energy level, so in which all the value of this n, they are identical, so and so. So all the basic vector psi m, so they have the same probability. So we can write down this value of omega of n1, omega of n2, so that is equal to this rho of En. So if all these systems, so they are considered as degenerate energy levels. Now let us say this is our equation number 7. Now for this microcanonical ensemble, if this system which has energy E, so which lying within a range, so for a particular specified range, so the value of this range in which we can write it as E plus of delta E to E minus of delta E. So this delta E, so that is very small as compared to this energy. Then the state of the system may be represented by the superposition of this basic vector psi of n, which belongs to these energy eigenvalue Em. So something like this, E of Em and Em plus of delta E. So for this microcanonical ensemble, which represents a closed and isolated thermodynamic system, so our density representation equations, it takes the form of rho of Nm, that is equal to delta of Nm into probability amplitude, so that is omega of n, and these having the value of 1 over omega. So for a energy value which varies from E less than equal to En to E plus of delta E, and that is equal to 0. So for our other states. So this is our equation number 8. So the value of this delta E, it is very small as compared to E, and this omega, that is equal to number of basic states psi n belonging to these eigenvalues En, belonging to energy eigenvalues En in the range E to En to E plus of delta E. So the constant, this 1 over omega, it results for this normalized wave function. So for this normalized condition, the value of this summation of omega n, that is equal to 1, that is the probability, it is a maximum value which is equal to 1. So this is our equation number 9. So these equation 8 and 9, it implies that for a system which is having energy values between E and E plus delta E, and all the density states, they belonging to set of E and delta E, they have the same probability omega n. So this equation 8 implies that for a system of having energy values E and E plus of delta E in this microcanonical ensemble, so all the states belonging to set E and delta E, so they have the same probability, and the probability is omega n, and this is equal to the postulate or prior probability, so which is equal to a postulate of equal a prior probability. So all these systems which are present particularly for this energy range, so they have the same probability. Now to study these implications of this equation, so we write down these equation in terms of a complex number. So when we write these equation in terms of a complex number Cn, so for this having particular alpha value, so that is equal to an of alpha into exponential of I theta of n alpha. So this is how we can show that it is having a postulate of random phase. So this is the expression or derivation for this second postulate of a microcanonical ensemble. So in this equation, the an alpha, they are real numbers, and this theta of n, so they are the phase angles. So therefore density matrix, so this can be written as rho of nm, that is the summation of probability p alpha into this canonical delta function. This can be written as cm star of alpha into cn alpha. So putting the value of this cm and cn, so this equation becomes p of alpha. So this amplitude, so this is equal to am star an star, so this is n, no sorry, an of alpha, this is not star, this is not complex conjugate, into exponential of I of theta n alpha minus of theta m alpha. So this equation becomes p of alpha am star of alpha into an alpha cos of theta n alpha minus theta m alpha plus, so opening the value of this exponential, that is equal to sine of theta n alpha minus theta m alpha. So this equation we can write down as summation of p alpha am star alpha into an star alpha cos of theta n alpha minus theta m alpha plus I sine of theta n alpha minus of theta m alpha. So actually, so since these amplitude they are real number, so the value of this am star alpha, that is we can write out as am alpha. So these equation, so let us say this is our equation number 10. So these equations, they are similar and agree with these equation number 8. So they commute, or we can write this something like Cn alpha square, that is equal to 1 of omega. So for all these values of the system n which are belonging to this set E of En to E plus of delta E and is equal to 0 otherwise. So if we want to reduce this density matrix function rho of nm is equal to rho of 0 into canonical delta function of delta mn. So we must have these amplitude an cos of theta n alpha minus of theta m alpha, that is equal to 0, and similarly a of m into an sine of theta n alpha minus of theta m alpha, which is equal to 0. So these are when m it is not equal to 0. So otherwise they will commute and our density function it will be equal to 0. So this equation, so it must hold for these density matrix. So when they are having diagonal density matrix, so this is the postulate of equal a prior random phase. So this is postulate of random phase. So these are the two postulates, that is equal a prior probability and random phase. So they are the basic postulates of this quantum statistical mechanics for this microcanonical ensemble. So similarly you can find out the density matrix for this canonical ensemble and grand canonical ensemble. So density matrix for a canonical ensemble, so this we can write down as rho of nm, that is equal to probability omega m into canonical delta function sigma nm. So that is equal to exponential of minus en over kt over summation of exponential of minus en over kt into delta nm. So let us expand these operator exponential of minus h over kt in powers of h. So then we can write down, so this exponential this h, that is the energy operator, which is equal to energy eigenfunction En. So E minus of h over kt, so that is equal to 1 minus h over kt plus 1 over 2 factorial h over kt square, so and so. So this we can write down as a summation of n, which varies from 0 to infinity, 1 over n factorial minus of h over kt raised to power n. And this satisfy the equation number 1. So therefore we can write down exponential of minus h over kt into psi alpha, that is equal to e raised to power of minus e alpha over kt into psi of alpha. So this is the same representation of equation number 1. So from this the density matrix, it is a function of this energy function h, and it can be written as density of h, that is equal to exponential of minus h over kt over canonical trace of exponential of minus of h over kt. So generally we write this trace function as tr within the bracket. So this we can write down as exponential of minus h over kt over trace of exponential of minus h over kt. So this the denominator term, so this is generally known as the partition function. So this density matrix, this can be written as exponential of minus beta into h over qn b, where qn that is known as the partition function of this canonical ensemble. So that is equal to exponential of minus of beta h over trace of exponential of minus of beta h. Therefore, we can write down the expectation value of any physical quantity which we can interact with these energy functions. So the expectation value of any physical quantity, so let us say z, and the energy eigenvalues of this g, so that is trace of density and g. So this we can write down as trace of exponential of minus bh over qn b into g operator, that is trace of so that is equal to trace of g e raised to power minus of bh over trace of e raised to power minus of bh. So this is the density matrix for this canonical ensemble. So similarly, you can write down the density matrix for this grand canonical ensemble. For grand canonical ensemble, so in this grand canonical ensemble, the density operator it operates on this Hilbert space. So with having an infinite number of particles. So this density matrix it must commute not only with this Hamiltonian operator H, but it must also commute with this number operator n, because we know that in grand canonical ensemble, so these number of particle these are being exchanged, so within these systems which are present within this ensemble, as well as the energy it is also being exchanged. So this density operator it is a function of this Hamiltonian operator h and this number operator n. So the eigenvalues of these operators it can be vary from 0, 1, 2 up to n. Therefore, this density operator for this grand canonical ensemble it can be written as 1 over this partition function of this grand canonical ensemble. So which is having these microstates omega v and t into exponential of minus b into h operator minus of mu into n operator. So this denominator term that is known as the grand canonical partition function, and it is equal to summation of exponential of minus of beta into h operator minus of mu n operator. So this we can write down as summation of, so if h that is the energy function and it is represented in terms of r, and this n it is the number function which is represented in terms of s. So this we can write down as exponential of minus of beta into er minus of mu into ns. So that is equal to trace, so that is the total sum of all these values exponential of minus of beta h cap minus of mu n cap. So this is the partition function for grand canonical ensemble. So therefore the ensemble average of any physical quantity, so that is G, so it can be written as 1 over L mu Vt into trace of operator G into exponential of minus H cap minus of mu N cap. So that is equal to 1 over LVT trace of G operator exponential of minus BH into exponential of B mu N. So this can be written in terms of this fugacity. So that is Z raised to power of N into Z of N phi N into B over summation of Zn into Qn of B. So this Z that is known as the fugacity, so which is equal to exponential of beta into mu. So where while this Gn operator, it is the canonical ensemble average, and this Q of n, that is the partition function of this canonical ensemble. So this is all about these density metrics for three types of ensemble, that is microcanonical, canonical and grand canonical ensemble. So this is all about for today's lecture. So if you have any query, you can write down in the comment box. So in our next lecture, we will discuss various examples of these three types of ensembles and try to find the density matrix and the energy functions for this electrons which is moving in a magnetic field, and then we will derive the example of a free particle in a box. So till then, goodbye, see you in the next lecture.